Buffers are systems that contain the acid, a weak acid, and its conjugate base in substantial amounts. And because of the common ion effect, these two systems, these two components interact in such a way that they create a near constant hydronium ion concentration. So it's very useful for us in having essentially a fixed pH through this buffer. So how do we make a buffer? Well, there's two ways to make a buffer. First is you take an acid and you dump in its conjugate base, and voila, buffer. The other way is partial neutralization, like we do with titrations. So let's look at the simplest way. You have a buffer system that is 0.05 moles of sodium acetate, which I'll just abbreviate NOAC, and acetic acid. You have 1 liter of a 0.10 molar acetic acid solution, which I'll abbreviate HOAC. And this is controlled by the following equilibrium. HOAC plus water goes to OAC minus plus H3O plus. Well, this is just our weak acid equilibrium. Ka equals OAC minus H3O plus, all divided by HOAC. Now, unlike our typical weak acid problem, where we just have this acid dissociating, here what we've done is we've added acetic acid. So our initial starting conditions are different than what we'd expect. Our initial values here is 0.1 molar. Our initial value of HOAC is 0.05 moles in 1 liter, so the molarity of this is 0.05 moles over 1 liter, which in this case is 0.05 molar. And so this is 0.05 molar initial. And then this is whatever it normally is. Because these are weak acids and bases, we'll lose a little of the acetic acid and we'll gain a little of the, and the rest will be released as proton. Now you could have done this with the negative sign the other way, it wouldn't have really mattered. And so we can plug these into our K statement and get an expression. But these are weak acids, weak bases, so this X will be small. And so we can simplify this. This will become approximately equal to the nominal concentration of the acetic acid, the initial concentration. Same too with this one, the initial concentration. So this would be equivalent to Ka is equal to 0.05 molar, because this plus X simplifies to just X, because this plus X simplifies to 0.5 molar, but this X stays the same, divided by our initial concentration of the other, 0.10 molar. Again, these approximate the initial concentrations at equilibrium because of the small x. Well, once we have this, it's very easy to solve for x, and we can get a value out. Ka we can look up from the table. This is acetic acid, so we know it's 1.8 times 10 to the negative fifth. And then we can plug in the rest of the values, 0.05 divided by 0.10 times x. And we get a hydronium ion concentration equal to fifth, which we can convert into pH, taking the negative log of this value. Of 4.44. So that's using an ice table. It turns out there's a simpler method. That's called the Henderson-Hasselbalch equation. And it uses the same approximations and the weak acid information. Henderson-Hasselbalch equation, the Henderson-Hasselbalch equation is equal to the pH at some value will equal the pKa of the conjugate acid plus the log of the weak base, the conjugate base, which in this case is OAC minus, and the acid form, HOAC. Now, again, because these are weak acids, these are the values at equilibrium, this would be minus x and plus x, but because the x is typically small, the amount of each of these would be approximately equal to the initial amounts in this particular example. And so, pH will equal to pKa. The pKa of acetic acid, Ka is 1.8 times 10 to the minus fifth. The pKa, the negative log of that, would be 4.74 plus the log of concentration of the conjugate base, 0.05 molar, divided by the concentration of the conjugate acid, 0.100 molar. And from there, we get the same idea, 0.5 divided by 0.1. This is equal to 0.5, the log of which would be this value right here, would be 0.301 negative. Add that to this, and we add the pKa to this value, you get plus 4.74 is equal to 4.44, just like our previous example. Right? So a little quicker, but just remember that you have to use the correct concentrations. So one way to work with buffers.